welcome to the first of our seminars. We're running these every Thursday at about the same time, barring diary accidents, etc. This one is about protection, or HV or MV protection. We call it MV protection. It's going to be an introduction to the subject. It's not intended to go into anything too deep.
Hi Nick, you got on mute again.
What's going on here? Right, it's now off mute. So a little bit about myself. I joined in Schneider in 2004. I'm currently the marketing and training manager within the power systems division of Schneider Electric. You can see what I like to do there, what I'd like to do, and I'm looking forward to retiring at some point in this decade. So that might give you a hint as to how old I am. However, protection, electrical protection. We take protection for granted in every aspect of our lives, and electrical protection is nothing new. We're all used to the 13 amp fuse that goes into the plug. How often those blow, I really don't know. I can't ever remember changing a fuse in the last 5 years because it's blown. Things are becoming a lot more reliable and a lot more safe. When we look at overall protection within our own homes, we have a series of MCBs, or if it's a really old distribution board, we've got fuse wire. But essentially what we're saying on here is that whatever we're using as protection, it is the deliberate weak link. And that weak link is designed to operate before something else will potentially fail, and that potential failure may be catastrophic. We always say that swapping out a piece of fuse wire for a 6-inch nail is the best form of protection. A 6-inch nail will take many thousands of amps to actually melt it, so it's literally adding another big link in the chain. So when we start to look at why we need protection, electrical faults can be really dangerous. When we start to look at cables, transformers, switchgear, when we ramp up the currents, we're ramping up the heating effect, because basically cables and copper and aluminium are just big resistors, albeit that the resistance values of copper and aluminium are very, very low. That's why we use them as conductors. But they are basically going to create a big heater. So anything within a HV switchboard or a transformer where you've got actual connections or wires or such like that are in close proximity to each other are going to potentially create hotspots. Now, one thing that we don't associate electrical faults with is mechanical stresses. And switchgear literally may try and jump around given the electromechanical energy which is generated in there. And when I say cables can wag, this little video here is from a laboratory. I haven't said where it's come from. I've omitted that. It's from a YouTube video of cables under test in the lab using a very high voltage as fault level passing through it. So you can see how they are literally jumping around, causing the cable tray to twist and bounce around, when in real life that cable tray may seem fairly rigid. So that's no different to switchgear or transformers. So inside a transformer, you've got a series that you've got one pole per phase, which will comprise of 2 sets of coils, and once you start to get those reacting, they can literally twist and things can get really distorted inside a transformer. So we've got to be mindful not only of the electrical damage but any potential mechanical damage. So what we want to start to think about is what potentially may happen. and these two images here, again, sourced from Google, are very extreme, which, if we don't do something about the fault in a relatively short space of time, that's literally what could occur. So the switchgear on the left, that, yes, that could be replaced in relatively short space of time, in say weeks or maybe months, but the transformer on the right, which on the face of it looks to be a 66 or 33 kV step down transformer, may take many months for it to actually get replaced, and may potentially cause significant downturns and outages in supply. So what are our overall protection requirements? Well, the bullet points that we've got listed there, obviously we need to detect. Detection is the first form, and then isolating the fault using whatever means we've got there. Safeguard supplies, minimize damage, ensure safety of personnel, all those key things there may not be used for a long period of time. And that may be months or even stretch into years. And when we start to look at electrical, HV or MV electrical networks, what we don't want is the protection actually operating every week, every day, every month. That would cause significant interruptions to possibly our daily lives. Just taking your own home environment, when was the last time the power went off from your DNO? And they've got a legal responsibility to maintain a relatively good power supply, and they're constantly looking at the protection side of the network, right from 132 kV all the way down to final distribution at 240 volts. So when we start to look at our protection devices, we've got three main areas. We've got traditional fuses. These are the HV fuses, which came in various different sizes. That was the traditional form of protection for distribution transformers up to about 30 years ago. Then we moved into two classifications of equipment called primary and secondary distribution switchgear. When we start to look at the two types of equipment, they've both got very different requirements. So if we start to look at secondary distribution switchgear, this is the likes of your classical ring main units or simple switchgear, which is not going to have great requirements on protection or control. So the protection requirements within those types of equipment are going to be very relatively simple. So we've got time limit fuses, or we've got self-powered relays. Sometimes we need a auxiliary powered relay as well, so dual powered. So the primary protection is self-powered from the CTs, and then for other functionality within that relay, it would need an auxiliary power supply. When we move into the more technical switchgear, this is going to be your primary distribution switchgear, whether it's going to be 33 kV or 11 kV or 6.6 kV, where the technical requirements are much greater. You may need a much higher fault current protection, so above 21 kA fault level, for instance. You're coming across protection schemes which are ranging from relatively simple to something which is quite complex. And this is where we start to see the auxiliary powered relays and brands of CPAM, MICOM, etc. Are now going to be used as standard within that type of equipment. It is incredibly rare to have self-power protection in primary distribution switchgear. Occasionally it does happen in some parts of the world, but certainly for the UK, we don't see self-power protection in primary distribution switchgear. So in all switchgear, whether it's going to be primary or secondary distribution switchgear, we've got this concept of where we've got the brawn, which is our circuit breaker. We've got some form of measuring, which is the current transformers or voltage transformers, or low power current transformers or low power voltage transformers. That's they're providing the means for the protection relay to work. And the reason we use CTs or VTs is to primarily step down the very high current flowing through the primary circuit to something more manageable. Protection relays are quite sensitive instruments. They don't like very high currents, and they certainly don't like very high voltages. And the stepping down from the high voltage and the high current is a safety aspect for the end user at the end of the day. What you don't want is your finger anywhere near anything above a few amps or a few milliamps, and you certainly don't want your finger anywhere any close to 11 kV. And the box, the compartment in the switchgear where the protection relay will sit is quite often referred in the industry as the LV box. It literally does not have high voltage in there as defined in the 18th edition, and it certainly won't have any high currents that you would associate with the primary circuit. So that's the concept. Now, protection relays come in different forms. For primary distribution switchgear, we're going to see a lot more functionality in the protection relay. So it's going to be might have logic in there. It might be connected to a communications and ultimately onto SCADA. If you're on SCADA, it's going to be sending alarms out if something's occurring, but doesn't necessarily need reactive action to trip the circuit breaker. And if you've got the right kind of relay, you will ultimately be able to retrieve what's been going on with it. I'll come on to more as to what we can do with protection relays as we go through. So here's the basic principle. We've got our protection relay, we've got a sensor, we've got a trip coil, and we've got a circuit breaker. So I always describe the circuit breaker as being the brawn and the protection relay as being the brain. As I've described earlier, the sensor is the link between the primary circuit. It's not directly connected to that circuit, and it's part of the chain. I always refer to it as the protection chain. So we've got the elements of our sensor, which is there. We've got an electrical link to the protection relay. Then we've got an electrical link to our tripping coil. The tripping coil, incidentally, is going to be housed inside the circuit breaker itself. The circuit breaker typically will have very strong springs inside it, and you will find the bigger the current, or the larger the voltage, the higher the voltage, the bigger the springs are going to be, because they need that amount of force to open the circuit breaker or close it. So we use springs for closing as well. So our trip coil is embedded inside the circuit breaker. It is the mechanical means to release the stored energy of the springs when the circuit breaker is closed. So any one of that chain can fail, and there are supervisory circuits that are built into the protection relay, and you can have additional relay which will supervise the whole protection chain, right from your CT through to your relay, through to your trip coil, through to the actual circuit breaker and position of the circuit breaker. So when we have got our circuit breaker closed on a healthy circuit, everything's hunky-dory. It's supplying information back through to the protection relay. That protection relay is constantly monitoring, and it's constantly looking out for information coming back from the sensors as what's going on with the network. So if we get a lightning strike, for instance, on the ground, we may get a very high voltage that will somehow flow through into the network and if we're using VTs and we're using voltage protection as well, then the VT will pick up a voltage rise, and if we've got that particular protection scheme in play, it will then trip the circuit breaker because of a very high voltage rise. But here I'm using the example of a very high current. So we've got our JCB, which has come along digging a trench, happy, or everything's happy until they see a piece of cable at the end of the bucket. It's chopped through the cable. That's caused a fault on the cable. So what we're going to see is high current flowing to the point of the fault. The sensor will pick it up, translate that into a much lower current, and then our relay, which is constantly monitoring that, will pick up, we've got a very high current, and ultimately it's going to decide what it's going to do. If it decides that the fault is going to be a permanent fault and is there for longer than what we've programmed the relay to in for it to actually work, then hey ho, it will then set in a chain where it will send a supply or a trip signal to the tripping coil, which will then open the circuit breaker, and provided everything is in good working order, and this is where maintenance comes in, the circuit breaker should then open. Occasionally, because of various things within the circuit breaker, it might be age, or it might be a very poor environment for the circuit breaker to be working in, i.e. a rail environment where you get a lot of dust and muck, the circuit breaker may actually trip, sticking closed. Therefore, in these circumstances, we would ultimately need the circuit breaker above that to work. And if that one fails to work, then we would need the one above that one to work. So this is why we need the ones in the whole system to be able to work and protect the one from the downstream of the fault. So I'm going to now look at time limit fuses, and we've got an image there of a ring main unit. Ring main unit's used in the UK. The specification is an outdoor piece of switchgear. That's because the majority of the DNO's ring main units may actually need to go outdoors. We do have an awful lot of outdoor substations here in the UK. But the TLF protection was developed in the 70s, as we can see there. It's very much the accepted norm with ring main units for the DNOs. You could probably say that about 80% of all ring main units that the DNOs use will use time limit fuse as their protection. The remaining 20% are going to be used for traditional protection relays like VIP or the Micon 116. There is actually a SIRED paper on this form of protection, so internationally it is known but not widely used outside of the UK. When you start to look at the protection, it is incredibly simple. It's very simple to see, it's very simple to replace, and the actual schematic that we've got there is relatively simple compared to primary distribution. You've got your protection CTs. They are ultimately will power the trip coils. We've got 3 trip coils, and we've got, showing there, we've got 2 fuses which are in parallel. The principle of operation is very simple. If the secondary current out of the CT exceeds the fuse size, then because of the resistance or the impedance of the coil and the impedance of the fuse impedance is much lower than the impedance of the trip coil, so therefore the current will flow through the fuse. Naturally, if the CT current is higher than the fuse size, then the fuse will blow. And then once you've blown the fuse, then the only path for the current to flow is through the trip coil, and then the trip coil will operate. And because of the tripping platform, it's going to open up all 3 phases. You see on the picture on the right hand side there, The fuses are really small. They're not as small as a 13 amp fuse, and they don't look anything like a 13 amp fuse, but they are. We've got various different sizes. Just to explain what we've got on here, we've got our earth fault pins there. So if the consultant or the protection engineer decides he needs to increase the fault current on earth fault up, then we'll fit a fuse to cover that. Down here we've got a shorting links for our CTs, because it's standard to fit dual ratio CTs for this type of protection. I'm going to come on to that one on the next slide. So that's what it will look like in practice. Very simple fuses, very simple to change, and the only way you're going to know if it's blown is by the circuit breaker being tripped and the trip flag on the front of the ring main unit. So this is the chart for selecting the appropriate TLF fuse for a given transformer size. You notice there we've got the CT ratio as a choice. On some of them you've got the choice, and others you don't have a choice. And the maximum fuse we can fit on time limit fuse protection is 15 amps. This is something that the ENA, which is Energy Networks Association, have actually agreed amongst themselves, and is very much in use with the DNOs and with private networks as well. It is a recommendation. The final choice is going to be down to the consultant or protection engineer to determine the right size fuse, but you are limited on the number of fuses available. It's also very good for coordination on the LV side of the transformer when you've got fuses as the first form of protection on the LV distribution. It becomes more problematic when you've got an ACB. You tend to find problems with coordination with an ACB and time limit fuse. So under those kind of scenarios, then it would be the best path would be to move to a self-powered relay like VIP or MyCom. But there is then becomes the aspect of, have you got enough primary current flowing through the ring main unit to power the VIP relay? And that's another subject entirely. So these are the benefits, these are the disadvantages. At the end of the day, the choice is down to the end user as to what they want. If they want something simple, relatively cost effective, then time limit fuse is the way forward. If you need something a little bit more sophisticated, then you're going to need to move to a protection relay. Now, moving on to protection relays, and this is now into the scenario of primary distribution switchgear. They've moved through various technological changes. So changes in technology have occurred in protection relays, tend to be a little bit slower than what we would experience with our TVs and mobile phones. Apple, for instance, will bring out a variant or a new phone every 6 months, 12 months. Variable speed drives, you'll get changes in variable speed drives every 6 months or every year. With protection relays, we tend to be a little bit more conservative, and some of the DNOs, hand on hearts, they would prefer to go back to the old technology, electromechanical relays, really robust. They were basically the only protection relay going if you go back in time. Now, moving forward into the future, one I've put there is server or mainframe, and that's looking forward to the future, and that future will be 10, 20, 30, maybe 40 years in the future, where we won't see protection relays as we would know them today. We're going to be seeing a computer doing exactly the same job, and it may be one computer or mainframe which is going to be looking after a whole raft of different circuits. we are using software now in protection relays. So it's just a natural progression, as you might call it, over to computer technology and away from hardware in circuit breakers. So we can see there are 3 pictures showing basically the advances in technology that we would see in the market today. Now, all companies, and Schneider is no exception, relays have moved in technology. In 1886, we can trace back to the portfolio within Schneider. ABB and Siemens will have a very similar picture. Relays throughout the world will have emerged from round about 1886, when the first relay factory was started up in Paris. That date there is also quite interesting, that the first transformer went into service around about 1887. That will be in America. So things are tying up together in round about the same date. And then as electricity became more and more popular, obviously relay technology moves on. So we can see there, as we've moved on, we've got 3 companies eventually merging into one, and CPAM, MICOM and VAMP form part of the overall Schneider portfolio of relays. So moving back to electromechanical relays, these are big, and you didn't get one relay that did everything in those days. So for the basic protection of overcurrent and earth fault, you needed 3. So 2 did overcurrent, 1 did earth fault. So that is very similar to what we've just seen in time limit fuse. So we've got 3 relays, we've got 3 trip coils, and ultimately we've got 3 CTs. Now, it's not surprising to find out that there are literally hundreds of thousands of these still in service today, and it's only in a relatively short space of time that London Underground moved over to the modern digital relays with when they were upgrading their entire electrical infrastructure. The nuclear power plants that we have in service today, they're still using electromechanical relays. They do require maintenance, so you need to take the circuit. You need to take the protection relay out of service, open it up, check and clean. This is where we get a lot of secondary injection testing to make sure that the coils are still working okay, and there is the obvious danger there that you're going to knock some of the components within inside the relay, i.e. springs. If you knock them off and don't put them back, then the relay isn't going to work as you would hope it was going to work. But they are still very, very robust, and there is a factory in India which is still manufacturing these kind of relays for either retrofit or for customers if they prefer to use them. When we look at the relay in a little bit closer detail here, we've got your CT coming, your secondary side of your CT coming in. We've got there what's called a plug bridge, so you can change the sensitivity of the relay depending on where the plugs go. We've got coils, we've got a disc with a peg, and the key is the peg. The peg is fixed on the disc will rotate given a certain amount of current. The disc is held back with a spring, and the principle is the higher the current, the quicker the disc is going to move, and ultimately if the peg reaches the contacts here, then the peg will short out the circuit and the circuit breaker will then trip. What we've got down at the bottom here is our time multiplier disc, and we can change the time multiplier up or down. In this example here, it's 1, so it's at the furthest point, and when we move it to 0.6, the peg is moving to somewhere in this point here. So it's a lot closer to the trip contacts than it was if it was at 1. Ultimately, it's going to take a shorter time to actually get to the shorting contacts. And this is now bringing me into the subject of inverse curves. So if you take this mechanical example and injecting a very high current into the coils driving the disc, then the disc is going to get to the trip contacts very, very quickly. But if you inject a lower current, the peg is going to get there a lot slower. So it's working on a natural curve. And these are just 3 examples of the classic curves which we would see here in the UK. Other countries will have different curves. It depends on the practice that is for that particular country. These are IEC curves. The Americans have got a different set of curves for the ANSI NEMA. And these are the kind of recommendations that are given in IEC for the different kinds of curves where they're going to be used. So if we look at the extremely inverse curve there, it says ideal for transformers. Distribution transformers traditionally have been used on fuses for protection. And these are the HV fuses. And apparently the curve on a very extremely inverse curve is the same as a curve used in the fuse. So that's probably why that one is recommended for transformers. But the principle here is, depending on which curve you're going to have, and I'll just do a very simple drawing using my pen. So if we take this example here of, and it's very, very straight line there. So if we take the inverse curve, the standard inverse curve, that's going to have quite a lengthy tripping time. If we move to the next curve there, the variance curve, a very inverse curve, we've got a shorter tripping time, and the extreme inverse curve, we've got a very, very quick tripping time. So it's how the curves are used, depending on the characteristics of the network and how we're trying to coordinate various different circuit breakers together. Now, and again, I'll reiterate this, it's not for me to determine which curve is going to be appropriate for which application. There are 2 other tripping characteristics that can be employed. One of them is definite time. So here we have a tripping time which we set. We will also have a set point for the current. This is the set point current. So that's going to be a constant tripping time, irrespective of what the current is going to be over and above the set point. So this will be a constant time there, irrespective of how high the current is going to be. The other one is definite time, sorry, instantaneous. So here we've got a set point. So it could very well be 100 amps. So it will send a tripping signal to the circuit breaker instantaneously from at 100 amps or above. And this is where the juggling now starts, because under various applications, you may decide to choose that you're going to use 1, 2, or 3 curves as a combination. And we would have what we call 3 set points. So we've got 1 set point when I get my laser pointer. We've got 1 set point here. We've got a second set point here. So we've got 1 curve on the first set point, then we've got a second curve on our second set point, and we've gone for instantaneous on our third set point. And these are the programmable characteristics you can put into a relay. And again, I'll reiterate, this is not for me to determine what that curve is what the combination of curves are going to be. That will be done during a protection study. Now then, when we start to look at various different circuit breakers and various different curves. So we've got an example of 4 circuit breakers with 4 protection relays. Starting at the top with D, that's our supply, so that could very well be our DNO circuit breaker, which will have its own tripping characteristics, its own curve, its own time delay. So that is our starting point. And when we start to look at C, we've got that curve there, so we can sit that nicely there. If we've got, when we've got move to B, we've got that one there. So everything looks on the face of it, looks okay. But when we move to A, that potentially is getting into an area where it may not actually be practical for the circuit breaker to work in the time that we would expect. So this is where the juggling act starts, when you start to look at a network and how many circuit breakers are in one particular circuit, or your LV devices as well. I haven't touched on LV devices and LV coordination. So what we've got there, we've got the dangers. So we've got to have a safety margin between each curve to allow for overshoot or allow for errors. We may end up with a case that I've said just a minute ago, where it's we don't have that amount of time margin, and it can become impossible to do any good coordination between our different circuit breakers. So, touching more on what protection relays are. So, the picture there on the right is showing one of the more recent protection relays. We're introducing colour displays into there. We're introducing tricolour LEDs, so you don't just get an LED which pops on with a solid colour. You can actually have them doing all sorts of things, flashing different colours. So you could have green when it's healthy, you can have it amber when it's an alarm, and you can have it red when it's a problem. You can also do logic programming in these, so the relay will go through a certain set sequence of logic with other relays when they're tied together. So you can have auto changeover schemes, you can have blocking schemes, etc. Because you're going to have amps coming in, or you might have volts coming in, you can have metering in there. Now, a word about metering: it is not what you would expect out of your separate meters. They are working on really accurate CTs. The accuracy of protection CTs is quite low because the CT has got to work on a very, very wide current range from normal through to fault current, whereas a metering CT only needs to work on its normal current range from, say, 10% above normal, what would be classed as your load current, your normal load current, down to, say, 80% of its load, and you would have really accurate measurements. You can also do a lot of diagnosis with these. So when we look at the fault diagnosis, what the relay is doing is recording a waveform as the fault is occurring, and that is you can set that for a very short time span, 1 second, or you can increase the amount of time that it's going to record, and you can extract that file out for a much more detailed analysis. You can also hook these relays up now onto communications network for remote monitoring, remote changing of the settings, and remote downloading of any event logs or fault analysis. We're bringing in now into that is the security of access into the relays, and cybersecurity is one of the big things at the moment as far as security goes. And these devices are now cyber secure, and you can limit as to access as to who is going to gain access to that. Also, if you want to have remote operation but near field remote operation, then that is coming into being as well. So let's look at a discrimination example here. We've got an incoming switchboard, we've got a generator, incomers there, we've got a switchboard which has got two bus sections. Both look as though they're going to be closed. We've got a ring feeders there as well. We've got three substations which have got redundancy built in. So we've got number one substation, for example, with two ring main units with RMUs on there, and then when we go onto the LV side, we've got the LV devices. We've got the primary LV protection, then we're going downstream onto the second LV device there as well. So what we would do in a very simple scenario on this one here, we would look at this area here. We don't need to worry about that bus section because there probably isn't any protection on there. So we're going to be looking at this area here for this particular example. In the overall grand scheme of things, consultant would also have to consider this aspect as well, alongside all the other substations, to determine what the overall fault level is going to be, not only for the main switchboard and the bus bar inside the main switchboard, but also the ring as well, what the fault level is likely to be on that one. One thing to highlight on here, when we've got high voltage or medium voltage generators directly connected onto the switchboard through a circuit breaker there, is that potentially that could increase the fault level over and above what the equipment with electric.
Terms and Windows download from
Hello.
download original software no download software.
Okay, I'm going to continue with the example. So now I'm going to break that out, what I've just highlighted there. And this is the kind of protection study which has been done on that particular area I've talked about. So we've got our ring main unit, we've got our C-boards feeding circuit breaker curve there. That is fixed and non-negotiable. So the DNO will not move because they've graded on their network right up to 132 kV. Then we've got our incoming circuit breaker there, which is our first circuit breaker. So that is that curve there. So we can see we've now got a difference in curves. So we've got standard inverse on the DNO, and then we've got our incomer A on very inverse. We've mirrored that on the ring switch circuit breaker there using a very inverse curve, and there is safety margin between the two. So we don't have our first curve on our first circuit breaker crossing over our DNO circuit curve. We don't have our second circuit breaker curve crossing over the first one or over the DNO circuit breaker. Now we're moving down to our ring main unit circuit breaker curve in the protection relay. Here we're using a very inverse curve, and this is a VIP 300 relay, which is on that particular one there. We can see there we're using a 2 set point setting. So we've got the first set point here, and then we've got the second set point here with a definite time curve. So we can see how it follows there and then drops down, mirroring the LV. Now there is a slight problem here where we've got the LV crossing over the HV. This would have to be taken into account when doing this study. It may be acceptable. It is the first LV device, and there is intertripping in this one, so it may be that it's acceptable. It may be deemed unacceptable, and then the juggling would then need to be taken into account, where changing the curve parameters on the VIP 300, which is doesn't have really fine setting. You can't really do fine settings with it. It's like you can do with a MICOM or a CPAM or an ABB relay, for instance. But this is one of the things that you would need to consider. When you take into account transformers, because of the very nature of a transformer, we've got to take into account where is our transformer inrush peak going to be, and they put it on the transformer inrush there on the HV side as being below the ring main unit curve. If that transformer inrush point was higher than the settings on the VIP 300, then we've got the potential for nuisance tripping. Every time we switch the transformer on from cold, then we were likely to see a nuisance tripping and then somebody having to go out and reset it every time. So that's how it all works in practice. Now, when you get a decision to make, and this is an example where I'm showing where you've got a time limit fuse and a VIP. So this first picture here again from Amtech, which is one of the proprietary software which is used for protection studies for both HV and LV. We've got the red in for time limit fuse. We've got green for your first LV, and then you got blue for your second LV. You can see there that the green is crossing over into the red, and then the blue is also crossing over into the red as well. So we've got a potential problem there. Just by changing from time limit fuse to VIP, we can manipulate the protection curves a lot easier. So we've gone for an inverse curve and a definite time curve, and we've got good clear coordination between all three devices. So this is where the juggling starts, and again it's down to a protection study which will determine which is the best way forward. Now, when you've got loads of circuit breakers, and I'm going back to an earlier example I was showing there where we got 4 circuit breakers in one circuit, and I was highlighting the fact that the curves may become too close together and we may not have any safety margin. There is a trick up the sleeve where you can hardwire the relays together. Admittedly, it's another piece of the installation that would need to be taken into account, but you can actually now set all your tripping times to be exactly the same, but you need to program the logic into the relays to trigger the blocking signals to prevent the upstream circuit breakers from tripping when they should be remain open. So the principle is that A won't see the fault, B and C and D will see the fault. Because A hasn't seen it and B has, then B will then send a blocking signal to C, and then C will then send a blocking signal to D. D and C will then remain closed, and C and B will then trip. That's the overall principle of it. But you will need to do hardwire for each of the protection relays. Now, moving on to some more other forms of protection we've got for transformers, particularly on the larger size transformers, which are oil immersed or fluid immersed, fluid filled transformers. Buckhorse is they're referred to as a Buckhorse relay. It's not a protection relay in its own right. It's got contacts in there which will close, and then will close the circuit to the protection relay in the circuit breaker. So they do need to be hardwired to the circuit breaker which is feeding the protection relay. Now, they are very widely used on larger transformers. You don't generally see them on distribution transformers. In fact, it's quite rare to see them below a 2 MVA transformer size. But again, it's down to what the customer prefers. So some customers, irrespective of the transformer size, will have a Buckhorse on it. Now, with the Buckhorse, it has to be fluid filled, it can only be free breathing, and it has to have a conservator. Those are the non-negotiables. And the Buckhorse sits in a pipe between the conservator and the transformer tank. It will have an alarm contact, it will have a trip contact, and for low-level faults where you may just want an alarm, that's when it will trigger. And you can also collect the gas for analysis as well. for a high level fault where you're going to get hot oil and gases flowing quite rapidly from the transformer tank up into the conservator, that's where the trip contact will actually work. Whether they actually use mercury now in the modern ones, I can't comment on that, but you will find it will have windows in there so you can see whether you've got sufficient oil in fluid in the Buckhorse, and it will be as part of the transformer construction with a terminal box and then wide out to the appropriate point on the relay. And bear in mind that the protection relay may be a little different distance away from the actual transformer in the compound. Now, all protection relays work on protection functionality, and all protection functions will have a particular code against it. And the origin of these go back to 1927 and 2028 with the American National Standards. American National Standards basically are within the ANSI-NEMA area of the world, but it seems to be a method of determining what protection you want for that particular circuit breaker. So there's a set of unique numbers or codes. There is also going to be a series of letters as well, and sometimes you combine the numbers with the letters to give you a protection functionality. And I've put up two there, 50 and 51. So these are for overcurrent protection. So 50, it's using the instantaneous protection curve, and for 51, you're using a time delay curve. And there are other numbers for other protection functionality, and our protection relays can have a number of these already pre-programmed into them. And it's a case of when you're setting up the relay using the software, you can select the different protection Anticodes to do whatever you want it to do. So here's some of the common ones. So we've got 50 and 51, which I've covered earlier. Now we've combined in a letter with a number. This is earth fault, so we've got N, which is earth fault in high voltage terms, or if you go into the definition within the ANSI code, it actually says neutral. And on a high voltage or medium voltage network, we don't have a neutral, so we translate that to earth. And then we get G, which is sensitive earth fault, and I do have an explanation with the differences between the two, and I'll try and explain why we might use that in place of normal earth fault. And then you start to look at restricted earth fault. This is where you've got protection on the low voltage side of the transformer. It's where you've got the 4 CT on the earth or the neutral. And then we start to look at pilot wire or pilot wire protection, directional protection, where you might be concerned about faults running in not just one direction, but maybe the other one. Differential protection is where you're on transformers or generators or motors, where you're looking for a fault inside the transformer. So for transformer differential protection, it's one relay, but it's two sets of CTs. So you have a set of CTs on the primary side, and you have a set of CTs on the secondary side, and the software within the relay is looking for an imbalance of what's going in and what's going out. Under voltage or over voltage, that's where you're looking for faults on voltage. So you might have a set point as plus 10% of your normal network voltage, or 50% below your network voltage. So it's where you're going to be protecting the network against sensitive equipment which will suffer from voltage. And then transformer inrush current, you can have that on the protection relay. You can also do thermal protection on your relay, and this is by calculation. It's not measured, it's by calculation. And I mentioned trip circuit supervision. This is where it's functionality within the relay, but it's also a simple relay, which is can be working in parallel with the actual main relay. Now, earth fault, N and G. So earth fault, use standard 3CT method. You can get down as low as 1 amp. So I think for normal everyday applications, that's probably going to be acceptable. Where you get problems with earthing, or sometimes people refer to them as hot sites, where the earth path back to the primary transformer is very bad. One kind of application that springs to mind now is quarries, where you don't have a lot of earth there, you have a lot of rock, and you then get a lot of problems with earthing. Areas of the country which do suffer from this is like Cornwall. There's got areas in Cornwall which WPD use sensitive earth fault protection and detection. Up in Scotland, up in the mountainous areas, or Wales, where you've got mountainous areas, that's also can be a problem as well. Quarries, it did used to be part of the Mines and Quarries Act. One of the DNO protection engineers said it's the quarries tend to throw the sensitive earth fault protection back at them. So it's very much now seems to be that kind of thing. So for sensitive earth fault, we need the 4th CT, and that's the CT which will go around all 4 cores, all 3 cores, and you can then get it down to 0.2% of the secondary CT. So you can get down to really low earth fault current protection. And as it says there, high resistance earth grounding networks. So I'll throw open the floor to any questions. Will, is there any questions on the chat?
No, I'm okay, thanks.
Okay, right. I'll time for you to open your mics, and I'll take any questions.
Nick, it's Will. There are a few questions on chat.
All right. Okay.
Can you open it and see it, or are you not able?
Let's just see if I can actually open it up. No, it's not. Oh. See if I can get chat running. All right. Okay, so why can't we use overcurrent and earth fault relay inside time limit fuse? Well, you can do. It's down to the choice. The DNOs prefer time limit fuse, and they use that on their standard protection. With VIP relays, certainly the VIP 300, you've got to take into account the primary current flowing through the primary circuit. So on a VIP 300, you need a minimum of 20 amps in the primary circuit. So that is going to limit you to your transformer size. So we would say if you did for an 11 kV transformer, that's going to be 400 kVA in transformer size. So that's where your limiting factor is going to be. But if you use an auxiliary power relay, then the actual minimum current becomes quite small. The next generation of VIP relays, the VIP 400, it's got a minimum current of 7 amps. So the transformer size is actually coming down. 66 kV ring main unit cable termination. Right, so on 66 kV, you're going to be using, you're not going to be using ring main units per se. I'm not saying there isn't one there. It's into the high voltage protection. So you're going to be using distance fault protection. You're going to be using line differential protection on that one, I would have thought. So that's that kind of protection there. So distance protection is one form of protection you can use on that kind of network voltage.
Nick, if you scroll back up the chat, there's questions that came in earlier on.
I've just answered those. Oh, right. Okay. Yep. All right. Oh, blimey. Yes. Right. I've mentioned. So Neil Davis's question there. What's the primary current to drive a VIP 300? That's 20 amps. For a VIP 400, that's 7 amps. Has Schneider got time limit fuse for 66 kV? No, we won't have. We don't do 66 kV ring main units. Right, so MV switchgear, phase-to-phase minimum clearance on voltage transformer and current transformer. I don't have the answer on that one. I can't answer that one. I do apologise. We'll try and get an answer to that one on that one for you. What sort of very fast protection required to avoid personal injury when people working on dead stroke live switchgear and though people following isolation safety peoples? It's all about risk assessment. Now, you would, if I give an example of the DNOs, they use live line or hot glove teams. They are literally working on live circuits, so it's 11 kV or 33 kV. But they are working in very safe environments. They're properly suited up with the right protective gear. But in the protection relay settings, there is what they call work tag, which will change the recloser settings from multi-shot to single shot, and it will also go to instantaneous. So they will drop the protection settings right down to an acceptable level, and then we'll go to single shot and instantaneous. But I would say it's all to do with the risk assessment and such like. Sorry about the picture keeps moving out of screen vision. I can only apologise for that. My screen is fine. I'm driving the presentation, so it was fine for me, and I apologise if there was any technical issues that went on during the presentation. I think I've all right. So Hussein has asked a question: why do we only have 2 TLFs but 3 coils in total? On the diagram that I showed, and I will try and flick back through to it. Right, so when it was first set up on the Cleveland protection scheme, and there is a paper on this. I haven't had a chance to read it. We're using 2 for overcurrent, which is acceptable. And then the 3rd coil for earth fault is deemed that it will cover all scenarios of earth fault current. I'll try and dig out the paper and post it on the post it up as a technical explanation as to why that is going to be used. Interposing relays. I don't know the full technical answer on interposing relays. It's where you may want to drop the current down even further, or you might want to link 2 relays together in 2 separate circuit breakers. I'm sorry, I don't have the full answer on that one. Again, I'll try and find some information and post it up. Are there any questions on the phone? Right, just about to close this, but one thing I would like to highlight is our series is forming the full series. We're running through till July. Those are the subjects there. So the next one is going digital. So ADMS stands for Advanced I can't remember it now. Advanced Data Management System. I'd apologise for that one. My brain suddenly scrambled itself. So the next time you'll hear me is introducing you to the concept of what SF63 switchgear is going to be like in the future. So if there are no further questions, I will close the session down, and we look forward to you joining our next session next Thursday at 11 o'clock. Thank you for joining in.
Thank you, Nick.
Thank you.
Thank you.
Thank you. Thank you, Nick. Thank you.
Thanks much. Appreciate it.
Thank you so much.